Good afternoon, everybody. My name is Dima Shliktenko. I'm the director of the Institute for Pure and Applied Mathematics, IPAM, and it's a great pleasure to welcome you all to this public lecture. So probably some of you are new to IPAM. I just wanted to say a few words about what we are. IPAM is an NSF-funded mathematics institute. We're located on the UCLA campus, and normally we do things in person. The mission of IPAM is to make connections between mathematics and other fields. Those other fields could be more mathematics, or could be things like engineering or social sciences or medical fields. So in this particular case, this semester, IPAM is running a long program on autonomous vehicles. So it's, well, had it not been for COVID, we would have had the experts on autonomous driving congregating at UCLA, but right now we're congregating in a virtual platform instead. Anyways, the focus of the long program is to research autonomous driving and understand its impacts on society, as well as understand the engineering questions, mathematical questions that underlie both of these areas. So Benny Seibold, who is our speaker today, is an associate professor of mathematics and an associate professor of physics at Temple University, and he is the director of the Center for Computational Mathematics and Modeling. He is one of the co-organizers of our long program this semester, and so he's going to be giving this talk about how automated vehicles can help with traffic congestion. So without further ado, let me hand it over to Benny. Thank you so much. And Benny, take it away.
Thank you very much, Dima. Thank you very much, everybody, for being here. Welcome. Thank you, obviously, to IPAM, all the organizers, for putting this together. So I hope we can have a nice tour of traffic flow, traffic waves, and automated vehicles. So I call this talk The Frustrating Beauty of Traffic Waves and How Automated Vehicles Can Prevent Them. So I'll talk a little bit first about traffic waves, then about instability, which is an important point here. And as a creator of structure, not just traffic waves, but many other things in reality, and then talk about traffic modeling and simulation, which is one aspect of IPAM bringing together many scientists from different disciplines to understand things, and then the role of autonomous vehicles or automated vehicles in the context of these traffic waves and what one can say, and then conclude what this could mean going forward. So to dive right in, one phenomenon that many people probably have encountered when you drove is what people call the phantom traffic jam phenomenon. Essentially, it's a local slowdown, but there's no discernible cause. So you have to brake because the person in front of you brakes, you make the person behind you brake, and you look around and there's no discernible cause for this slowdown. And one can think of this oftentimes as, even if you initially have uniform traffic flow, it becomes unsteady, inhomogeneous, even in the absence of the obstacles. So unlike a traffic jam where you go fast and then you suddenly have to go slow, these phantom traffic jams are oftentimes traffic waves, in the sense of that you brake, but then very soon after that, a few seconds later, you accelerate again. What you see on the top right is actually a long exposure picture at nighttime, and you see that most trajectories are blurred from the lights you see, except for these vehicles that you see there. So these vehicles over the exposure of the image were stopped. And you see it's only a localized stopping. So it's a beautiful picture of such a traffic wave that has been taken. So these traffic waves are waves of brake lights that travel backwards along the road, and they're real features of highways. So they're interesting to study. But one should care about them more because they're unexpected braking events. So they're hotspots for accidents. They are wasting fuel because braking, accelerating is consuming much more fuel and driving steadily, and they increase emissions and therefore pollution in cities, which we'll also talk about later. And the most important part is, unlike large-scale congestion, which pretty much is insufficient supply of road capacity relative to the demand of people who want to use it, these localized features are in principle avoidable if everybody were to drive slightly differently. You could drive slowly but steadily. We'll talk about later, of course, how much one can do about that aspect. But in principle, they are avoidable by changing the vehicle dynamics. So research questions that the community is interested in is, of course, understand the underlying principles of these phenomena, reproduce them via mathematical models and computer simulations, and use that understanding that you can establish to eventually develop strategies to prevent those undesirable and avoidable features on the roads. So here's a video taken by Dirk Halving. You see that the traffic leaving the downtown area is flowing relatively smoothly and uniformly, but the traffic flow going into the downtown, there's congestion, there's stoppage of vehicles, but the stoppage is localized. So you do see that, you see it here in some spots. You see these waves that are traveling backwards, and they're waves of cars that are stopped, but the cars come to a stop for a few seconds and then accelerate again. So these are really stop and go waves. You see another one here on the screen. So these are stop and go traffic waves, and they're waves of brake lights that travel backwards along the road. Now there's a lot of things happening here. It's cars intermixed with motorcycles, with buses. You have on-ramps, you have off-ramps, you have lane changing. So it's not completely easy to pinpoint what exactly are the ultimate root causes for these phenomena that occur. Is it due to a lane switch, for example? Or would they also happen if you just had a single lane, no ramps, all passenger vehicles? Would you still get these stop and go waves, these traffic waves happening? So 2008, a group of Japanese researchers devised this experiment, essentially form a ring road of a single lane, and have drivers drive on that road. Initially, you see they start out uniformly spaced and driving all at the same speed. But it turns out that this uniform flow is actually something that the system does not dynamically like to have. The dynamics drive it away from that uniform flow. And instead, small perturbations that always happen, right? Little inaccuracies in the driving, little variabilities in the engine actually drive the system towards this traveling wave that you see now forming on the top right that now travels backwards. So again, you see that wave of stoplights forming. So this was the first experimental demonstration that in fact, these traffic waves, these features that many of us have seen on the highways, these phantom traffic jams, can in fact arise from the simple car following dynamics, the simple collective driving dynamics of the human drivers on the road. It's not that one person triggers it, it comes from the collective behavior of all the agents. So that, of course, is a very, very important fact and a very important observation. So you see that for a given vehicle density, the one that you have on this road, so the road has a certain length, you have a certain number of vehicles. So it's in this case, 21 vehicles per 230 meters. So for that vehicle density, it turns out that the uniform flow, the desirable flow, everybody goes at the same speed and is equispaced, is actually unstable. So the dynamics drive the system to a different state, not the uniform flow, and in fact, the traveling wave state. And this structure, again, emerges from the collective driving dynamics. So what is really forming these structures, forming these traveling waves here, is an instability. And instability is actually something that does not just arise here in traffic flows, but is really ubiquitous in reality. And of course, also is really interesting to describe. And in fact, I want to move forward by highlighting some of these aspects. So I call this section here, Instability, a creator of structure, because I really want to highlight how ubiquitous, how wide these instabilities are in practice, and how many phenomena and structures that we see are ultimately formed by instability. So what do we mean by instability? So there's the word equilibrium. Equilibrium essentially means that your system is at a state where the forces net out to zero. Yeah, so the simplest example is probably a pendulum, as you see in these two figures here. So the pendulum has two equilibrium states. One where it is just hanging down, and one where it is standing up, exactly straight. In both cases, the forces that act on the pendulum net out to zero. So if there were no imperfections, the system would remain in that state. But of course, there are always imperfections. There are always small perturbations. So what distinguishes stability from instability, so a stable equilibrium from an unstable equilibrium, is exactly how does the system react to small perturbations. So a stable equilibrium means that small perturbations decay. If you have a pendulum that's hanging down and you perturb it a little bit, the dynamics bring it back to where it started from. On the other hand, if you have an unstable equilibrium, like the pendulum standing up, then small perturbations amplify and drive it further away from that state and drive it to a different state, to some other state that is actually dynamically stable. So that is the concept of stability and instability. And instability is what drives and creates structure. So, for example, water waves. So obviously, if you're a surfer, like the person in the figure, you want water waves, right? So it's a pleasant thing that you want. How can you explain it? Well, you have an initially flat ocean surface, then you have some wind blowing across the surface. Now, to get the mechanism of instability, you always need to think, what if I had a small perturbation? So what if you had a little bit of a hump on the water? Very tiny. Well, what would happen is that hump now would provide more possibility for the wind to catch on. It would push the water sideways and therefore a little bit upwards, up the hill, and therefore amplify this crest, amplify and therefore grow it. So whenever you have a mechanism that if you start with something that's initially uniform and you perturb it a little bit, you have a mechanism that amplifies this perturbation, then you have the mechanism for creating structures, in this case, waves on the water surface. Sand dunes follow similar principles. So if you start with an initially flat sand and then you have a little bit of a hump, then wind blows sand, and once you have a hump, it acts like a little ramp and it can catapult sand grains upwards. This is called saltation, and therefore then growing the hump. Now, not every wavelength of humps does it, but there's certain wavelengths where they actually get a growth, and this can grow to sand dunes that are hundreds of meters high. Sea ice patterns. You see, for scale, the two humans on the left, you see that radiation melts ice, but it's not that suddenly everything is gone. Instead, you get these very intricate patterns of ice and ponds. Again, starting from a uniform ice pattern, now you have sun radiation, warming and melting. Now, what is the mechanism that leads to an instability? Snow is white, ice is white, therefore it reflects a lot of sunlight. The water is darker, so it absorbs more sunlight. So at the moment where you get a little bit of a small amount of water, that water now warms more than the ice, according to sun radiation, and therefore growing that structure that you had. So you start with a small perturbation and that structure grows, and therefore again you have the mechanism for an instability. Defrosting in a microwave oven. Why do microwave ovens have a defrost button? What the defrost button does is it essentially heats things slowly. It heats for 10 seconds and then it has 20 seconds break in between. If you didn't do that, what would happen? It turns out that microwaves heat liquid water much more efficiently than ice. So if you get a little bit of water forming, that water will be heated much more rapidly than the ice around it. So if you do it too quickly, you can actually get boiling water right next to ice. And obviously that would not lead to pleasant food. Fluids are a prime example where there's a lot of instabilities happening. For example, if you turn on a faucet, just slightly so, initially you get a stream, but at some point the stream starts forming bubbles and droplets. So you get droplets and break off. Again, what is the mechanism? You start with a uniform stream initially, but then you have some small perturbations to it, some small imperfections. But at the moment where the water stream becomes more narrow at a point, the surface tension contracts it more at this point than in the wider parts, and therefore amplifying the structure and eventually leading to droplets forming and breakup. Or you take a light fluid and put a heavy fluid on top. What will happen? The heavy fluid wants to get to the bottom, the light fluid wants to get up, and you get these plumes of fingers forming. That can happen in many fluids, like, for example, in our atmosphere or in a valley where you have inversion weather. But it can also, in fact, happen in huge length scales in astrophysics, like, for example, here, the Crab Nebula, which also has fingers that form due to fluid dynamical instabilities. Or, of course, beautiful structures like the Grand Canyon ultimately result from instabilities. You start with an initially flat terrain, and then you have a little bit of a dip, a little bit of a channel that's forming. Rainwater will, of course, then run into that channel and therefore deepen the channel. So initially you start flat, you have a little perturbation, and then this perturbation amplifies, and over a course of over millennia and then millions of years can form whole canyons that result from it. So there's a lot of structures, but also societal issues. We see instabilities all around. For example, bus bunching or subways. You might have encountered scenarios where you wait for a bus for quite a while, and then suddenly there's two buses right behind each other. So why would that happen? Well, it again can be explained through a dynamic instability. If you start out at the top figure with buses equispaced, then roughly you have the same number of people wanting to get on and off the bus every time you have a bus stop. But let's say now you have a small perturbation. So one bus, the one in the middle, falls slightly behind. Now what happens? Now you have a mechanism that amplifies that falling behind. Why? Well, if that bus is slightly behind, there's more time until that bus arrives for people to wait at the stop. So you see more people waiting here, but that means once the middle bus is picking up these people, they will take longer to board the bus. And therefore there will be more people on the bus eventually. Therefore, any subsequent stop, there will also be more people to board and more people taking time to get off. Whereas the bus behind will have fewer and fewer people in it, therefore catching up. And therefore you get naturally an instability. And initially equispaced buses will have a tendency to become less equispaced. Therefore, of course, to counteract this, at some point, the empty bus should overtake the full bus. Or sometimes in subway stops, people are being asked to get off the subway and wait for the next train so that the first one is empty and can start going faster. So these are just some examples of instability, but this connects traffic waves as a phenomenon with many, many other features in reality, and instability is really a creator of structure. So as a little homework problem, I encourage everybody to think about patterns in the world around you and think whether they could be caused by an instability. So again, you start with something uniform and you have a small perturbation, and this small perturbation can be amplified, systematically amplified, and then grow into patterns. Now, having seen or conjectured that traffic waves are caused by instability, can be caused by instability, of course, one needs to check whether this is plausible via mathematical models and also computer simulations. So traffic models and traffic simulation is something that transportation engineers, but also mathematicians, physicists, engineers are very interested in, because ultimately it's about understanding this real-world phenomenon. And when you say about developing models that describe or reflect reality or simulations, one can, of course, and should ask, what is the point of this? Why are they needed? Why don't we just observe traffic flow as it exists and classify what one sees and measures? And this is an important question. Why develop and study models of reality? That is not just a question for traffic flow. It's true about every system that is out there. Well, the first point is you can reduce system complexity. Most real-world problems are extremely complex, but in modeling, you can isolate a few key mechanisms and then test and understand whether they are the dominant mechanisms that form and govern the structure. What is important to remember here is the quote by George Box: all models are wrong, but some are useful. So the goal of modeling is not to describe every single detail about reality, but in fact find the simplest, conceptually simplest description that captures the key mechanisms that describe the phenomenon. So for traffic waves, of course, the question is, what are simple models that capture the instability and produce the wave behavior? Once you have a mathematical model and formulated a mathematical language, you can use computational resources to simulate the model and see what would happen if you, for example, changed model parameters. So you can calibrate your models to what you measure in the real world, but then study what if drivers were more aggressive or less aggressive? What if the vehicle mix were different? For example, thrown in a few more trucks or a few more automated vehicles. What if the road conditions were different? And you can understand which effects play what role on reality by modifying your simulation and your model. It can give you predictions, so you can forecast potentially what the traffic situation in your city will be in 15 minutes, in 20 minutes, and therefore get better travel time predictions. And also, it turns out that we don't actually exactly know how humans drive on average. So models that reproduce correct emergent phenomena like stop-and-go traffic waves, for example, instabilities, can also help us understand ultimately our driving behavior by proposing a driving behavior, analyzing the model, doing a simulation, and compare the predictions of the simulation with what is actually observed in reality. So the key step in developing models is, of course, to observe reality, to understand what are key mechanisms, what are key quantitative behaviors. Essentially, the father of traffic flow theory was Bruce Greenshields, that you see on the top left, who just 25 years after the first Ford T model, the first vehicles essentially used this new device called a video camera to collect data about traffic flow. And in the bottom left, you actually see what he tabulated. He tabulated the speed of traffic flow on the vertical axis versus the traffic density on the horizontal axis, and collected these data points. One here, one here, one here, one here, and then some congested data point, high density, low speed out here, and observed that they lay beautifully on a straight line. So in other words, the speed is some decreasing function of the traffic density. If you have more cars, the average speed of traffic flow is lower, and this is not just a qualitative statement, but a quantitative relationship. Of course, since then, traffic data collection has gone a long way. In the 1960s, loop detectors were put into roadways, like you see here, that count cars and flow rates and speed estimates. Of course, there's camera systems here, like in this case, this is from a 2015 data set that collects on a segment of highway the trajectories of all the vehicles that then can be used by researchers to get really fundamental insights into car following behavior and driving behavior. And then obviously disruptive technology was the fact that nowadays almost everybody carries a GPS transmitter with them, and we're willing to transmit our position in exchange for getting quality routing. And this, of course, can also be leveraged to get lots of information about driving behavior. Now, the difference here is that this was a transition to essentially mobile sensing, so in-vehicle sensing, whereas the traditional means were dedicated infrastructure put into place by agencies. Later, we'll come back to that point also from the point of view of traffic flow control. Now, once one has some relationship, for example, as we saw in Bruce Greenshields' measurement, you might have a relationship between, for example, the speed that cars would like to go and the gap between two vehicles. So what do we mean by this? You have one car following another car, for example, in one lane on a highway. The car, let's say front bumper is at a certain position. I call the position X. The car goes at a certain speed. Let's call this V. Of course, the car and the car ahead have a length, and then you have a gap between the cars. So how much open space there is between my front bumper and the rear bumper of the car ahead of me. And now I can collect data and see that to a reasonable approximation, I actually get a relationship between the speed that cars want to go and the gap that arises. If the cars are very close, bumper to bumper, that speed is 0. And then the speed increases as the gap increases up until, of course, the gap is so big that I cannot really go faster and faster, because at some point I would get a speeding ticket. So this, of course, will level out at the speed limit, or depending on where you are, the speed limit plus 5 or 10 miles per hour. So this is an empirical law of traffic flow that you could measure. And of course, real measurements will be clustered around here, but you could say this is an approximation. Now let's say this is our law. So we have a relationship in this car following dynamics where the target speed is just some function of the gap to the vehicle ahead. So now I can postulate a model. Let me do the following model. The acceleration of a vehicle is as follows. It's some constant c, and that constant c here essentially just measures how quickly drivers adjust. If c is big, you very quickly adjust. If c is small, you adjust very slowly. And what do you adjust? You take your target speed, your desired speed, capital V, that depends on the distance to the vehicle ahead. You compare it to your actual speed. And if your target speed is bigger than your actual speed, your acceleration is positive. You accelerate. On the other hand, if your target speed that you should go with, given the spacing to the vehicle ahead, is smaller than your actual speed, this acceleration becomes negative, and therefore you slow down, or if it's strong, you brake. That is a dynamic law of car following, of driving. And based on this car following law, you could now try to extract what are the consequences if you now have many vehicles on the road and you see everybody drives according to this law. Now, this function V, this C here, these could be uniform across all the drivers. They could be different for different drivers in different vehicles. All of this can be studied either by pen and paper in some simple situations, or once the situation becomes so complicated that you cannot solve it by pen and paper, using computer simulations. So if you have such a law, you could use a computer simulation. And if you program, you can actually implement this. It is actually relatively simple. Conceptually, you line up a couple of cars in a line, single lane, and use the fact that the velocity is the rate of change of the position. And the acceleration is the rate of change of the velocity. So acceleration tells me how much does my velocity change per given time interval. And now you use this fact to do an approximation to the model. You choose a small time step, say 1/10 of a second. And then you march the model forward using your computer. You say, given my current position X, given my current speed, I just update my position by just taking my speed, multiplying it by my 1/10 of a second, and moving the vehicle forward by that amount. And likewise, I update my speed by my acceleration from up here times 1/10 of a second and change my speed according to that amount. That is a mathematical approximation to this law. And with that, I can get approximate rules of how traffic flow would behave. And now this is a very simple model. Traffic modelers study this model, other models, much more complicated models. And many models have different usages of where they have a point, where they are being used in reality. But what is common is that they allow you to make predictions about what will happen forward in time, given certain assumptions about the driving behavior. For example, here, you can start with an equilibrium, like we had before, which means all vehicles are equispaced and all drive with the same speed. And then you add a small perturbation and study under this driving law, will small perturbations amplify or will they decay and keep the system close to that uniform flow equilibrium? And it turns out for this choice here, if that constant C is large, if drivers adjust quickly, then uniform flow is stable and the system will remain close to the uniform flow. On the other hand, if C is below a certain threshold, then in fact you get an instability. And since we know that traffic waves and instabilities and phantom traffic jams happen with real humans on the road, one can actually make this a model for reality by choosing C sufficiently small, but not too small, so that you have slight instability, and that is now a model for human drivers. So since this is a talk of a math institute, here are some equations. The rest will again be very pictorial going forward. So for example, here you see a video of such a simulation. At the bottom, you see what it means to the individual vehicles. At the top, you see what it means to the traffic density, to the vehicle density, which is this blue curve. And you see that this simulates the evolution forward in time. In fact, there's some theory that can be done that might even predict what this traveling wave will be forward in time. That's the orange curve. But you see that the vehicles here, whatever goes out on the right comes in on the left. So it's really a ring road that you have. The vehicles here form a traveling wave that goes backwards on the road. Every vehicle brakes heavily and then accelerates again. And there's a local region of where the vehicles are very slow. So this resembles really the ring road experiment done in 2008 by the Japanese researchers. So this really resembles in essentially simulation what one saw prior. Now, one has a model, and now this model, of course, can not just reproduce a ring road. You can also, of course, investigate what happens if you look at a really long road, 6 kilometers of road now. So 4 miles of road, you had a little bit of perturbation. You have a uniform state that is dynamically unstable again. So this small perturbations here increases the density. More cars get localized in a certain spot. You get this typical braking behavior here happening along the road. These are a lot of vehicles here. So these are zooms here, but these are a lot of vehicles down here. So it really makes more sense even to look at it on the level of the traffic density. Now this initial pileup, this initial wave now produces a dip downstream. That triggers another instability, triggers another traffic wave. This triggers another dip, another wave, another dip. So you get this whole chain, this whole train of baby waves being born out of the lead wave. Now, this model now has something to do with reality. It means that if you had a phantom traffic jam, you had to brake because the person in front of you brakes and you look around and you don't see any discernible reason. It is likely that somewhere downstream, 30 seconds later, 1 minute later, you will have another one of these sudden stoppages. And again, that oftentimes agrees with what is being observed in reality. But it also means from these models that all these drivers are actually identical and they behave exactly the same way and fully predictably. Nevertheless, you get uniform flow is unstable, amplifies, small perturbations amplify, and what you actually get is these stop and go traffic wave solutions. So they can arise from the collective driving dynamics of all the drivers on the road. You don't need any bad drivers who are at fault at causing these waves. Now, that does not mean that there are no bad drivers on the road, but it means that these phenomena can arise even if you have nobody being at fault at causing these waves. It's really collectively of us causing it. And one reason why we might not be aware of it is, of course, that what happens due to our driving behavior happens behind us, but we don't necessarily see the consequences of us amplifying wave behavior. All right, so this is what happens on real roads, and this is how we can understand what human drivers do. So now one needs to ask, what is the role of autonomous vehicles in this context? So a common impression of autonomous vehicles is that at some point they will be there, created somehow, and we will have suddenly all the vehicles being autonomous. We don't need to deal with the chore of driving anymore. We can lean back and enjoy that a car does the job for us. The reality is that fully autonomous cars that don't have a steering wheel, we can lean back, are really still a distant future. I will say on the next slide some reasons for that. But what turns out that if you talk about automated or semi-automated vehicles, there's a lot of very, very smart technology already in modern vehicles that one can buy, not just the high-end vehicles, but really consumer-grade normal vehicles have, for example, lane assistance. They have adaptive cruise control systems, a cruise control system that doesn't just keep a constant speed, but slows you down as you run closer to the car ahead, so you don't need to disengage it, even in heavier traffic. So there's a lot of potential due to vehicle automation and also vehicle connectivity, vehicles exchanging information with each other that can be explored and might actually modify the traffic flow, the way traffic flows in the near future. And particularly interesting, of course, here is the question, could vehicle automation dampen these traffic waves and prevent the instability from arising? So I said before that fully self-driving cars, what people call level 5 autonomy, mind off, there's even no steering wheel in the car, that definitely will not happen in the next 10 years. And a few reasons is just that human drivers are very good at interpreting context, and they know when to bend the rules. For example, is this a stop sign? Well, clearly it's a stop sign. And modern image techniques can probably recognize this as a stop sign. But is that one that one should follow? Probably not if you're a human driver, but think of all the possibilities of what could arise where the context information tells us how to drive, or we have a sixth sense that this intersection must have a stop sign and must have fallen off by the wind, for example. There are also examples where, in fact, small perturbations to stop signs in some computer perception techniques can even mislead the perception to thinking they're speed limit signs. I did not put a sign on here, but you can Google this and look this up. So there's a lot of challenges also in making computers perceive the real world in a way similar to what we humans do. It is a really, really challenging problem that requires a lot of work. Another aspect is that it's not always that the cars are amongst themselves. There are many situations where cars interact with humans. And especially in Europe, you have situations where there's not even clearly defined rules. You see, there's no clear separation between the pedestrians and the cars. There's sort of a common law type of understanding, but and humans adapted, but the drivers know what to do, but they're not able to formulate this and cast this into precise rules. So making a safe perception and algorithm and implementation in a fully autonomous vehicle that can do this is still something that development is not close to doing. And another aspect is also that this whole perception pipeline of cars seeing and interpreting results correctly is also actually quite energy consuming. So the total energy demand of these vehicles can actually be quite substantially higher than normal vehicles, which of course also in a sense defeats the purpose of the hopes of gaining efficiency through some of these vehicles. So this is the bad news. The good news is that to get substantial benefits to the efficiency of the traffic flow system, you don't actually need fully autonomous vehicles. So, for example, there's some really promising work on platooning trucks. So if you have trucks, let's say 4 trucks, and they all travel a substantial amount of their path, share the route, these trucks could wait for each other and then travel as a platoon. So you see here, they're really close to each other. They're just a few meters apart from each other. And the reason this works is that the trucks number 2, 3, and 4 are actually computer controlled. And they do it in a way that it is safe. By receiving signals from the truck ahead, I will brake soon, before they actually brake. And they can implement this in a reliable way. What are the benefits? Well, first of all, they use up much less road. Second, the air, rather than going in between the trucks and producing air resistance here, goes around the whole set of trucks. So it's more like a train with multiple train cars. And therefore, the total fuel consumption goes down substantially. And third, the drivers, the operators of the trucks behind, they still need to oversee the system, but they don't need to actually drive physically. So they're there as overseers, but they can actually rest during that time. That is, of course, far from a fully autonomous system that could handle situations like the ones here outlined on the right, but this actually is something that works quite successfully. And it's plausible that in the next 5 years, some of these technologies might be deployed to our roadways. Another aspect when it comes to passenger vehicles that has to be mentioned and remarked is that, of course, it's not that suddenly when there's an automation that everybody will adopt it at the same time. We're going to see the next 15 years of being highly heterogeneous systems out there in terms of what level of automation we see. And therefore, notions of that self-driving cars or vehicle automation will remove large-scale congestion, unfortunately, is too good to be true. You see it in this little depiction here, right? If your car can be as autonomous as you like. If you're stuck in traffic of traditional vehicles, you're stuck in traffic, right? There's nothing you can do about it if this is the only route that you need to take. So large-scale congestion, we still will need to deal with. But of course, maybe you have congestion, and instead of driving steadily, brake, accelerate, instead of driving unsteadily, you could maybe drive slowly but steadily. So the idea of dampening waves, of course, still has a lot of merit, which brings us back to our stop-and-go traffic waves. So ultimately, the idea or the question is, let's say we have just a few vehicles that have automation capabilities, say 1 in every 20 vehicles or 1 in every 22 vehicles, like here the simulation. Why that? Because it resembles the ring road experiment that we saw earlier. There were 22 vehicles on a ring. And now the question is, if you only have human drivers, we know that this will cause instability. What if one vehicle, and only one, had a smart controller that it has velocity automation, so it can choose its speed automatically based on sensing what the cars ahead are doing and the cars around are doing, in a way that it has the goal of dampening the waves? Now, of course, come the simulations and the models that we have, because now we have models, we have simulations, and we can test. So here you see twice the same simulation on the left and the right. You have 22 vehicles going around on a circle. The blue car is just human controlled the same way as the red cars. Now these models are designed and calibrated so that they reproduce the instability. So now you see that the system actually has caused an instability. You see the wave traveling backwards. But now what will happen at 120 seconds is that on the right, and only on the right, this blue vehicles will be turned over to an automated velocity controller. So you see it now at 120. So now the blue vehicle has turned over to a velocity controller that is specifically designed to dampen the waves. What is important is that the red vehicles have not changed anything about their driving behavior. They're driving by the same principles as they did before. But one vehicle driving in a smart way, constantly observing what the other cars are doing and aiming to dampen the waves, actually suffices at keeping the flow close to a uniform flow profile. And you see that this not only dampens the waves, it makes the average speed of the flow also faster, because this blue vehicle now is much more ahead than in the reference situation where you still have the waves. So this looked very promising. And it could hint that just at a few smartly controlled vehicles, you could really dampen these stop-and-go traffic waves in reality. Not get rid of large-scale congestion, but dampen these waves. But this was in simulation only. And of course, all models are wrong. All simulations have to be taken with a lot of care. Ultimately, you don't know for sure until you tested it on real roads, or at least in an experiment with real vehicles. So a research team went out. You see here some of the team members, including myself, in the desert of Arizona. It was in July in Arizona where this was carried out. So there's a lot of interesting stories about operating equipment at and humans at high temperatures. But we had a 360-degree camera in the middle. We had a traffic circle reproducing the ring road experiment that you saw before. We had sensors in the vehicles that tabulated the speeds and the fuel consumption of the cars. And we had one single automated vehicle here that by the student in the backseat could actually be controlled via his laptop, and control algorithms that were programmed specifically with the goal to dampen the waves. And here are the results of that experiment. So you see initially, every car, including the control vehicle, is human controlled. So you see that the instability kicks in. So we're reproducing the instability. Now you start seeing these waves forming. This is sped up by a factor of 6 here. So in reality, it was slower. And now the velocity controller is turned on. So the velocity controller tries to drive at a constant speed rather than following the waves, which means that in the beginning, when the cars ahead of you are accelerating, you don't follow the acceleration as much. And as a consequence, you see that it did reduce the variation of the speed. So the gray curves here are the speed profiles of all the cars, and how much they vary tells you how much the velocity variations are. And you also see in the video right now, this is the best controller here. Pretty much the car leaves a little bit of a larger gap, but ultimately it has successfully dampened the waves. And then you look at the metrics here and compare the situation where you had the waves, which is here in this regime where you have essentially going very fast and having speed 0, and compare it with the best controller that was tested out here, and can compare the traffic flow in terms of key numbers. For example, we measured the fuel consumption of all the vehicles on the road. That is important, not just the control vehicles, but all the cars on the road. And what turns out is that the fuel consumption is almost cut in half. It is reduced by 40%. So if you control for traffic waves and dampen them, you have about half the fuel consumption of the whole traffic flow compared to if you had these strong waves here. Strong braking is reduced by a factor of 70, so it's essentially cut to 0. The velocity variation, you see it here, is much, much less than you have here on the waves. And also the average speed of cars, similarly to the simulation we saw before, actually went down by, the travel time went down by 14%. So the throughput, the average speed went up by 14%. We also looked, based on models for vehicle emissions, on how this would now manifest not just in the fuel consumption, which we saw here was reduced by 42%, but also in terms of vehicle emissions. Vehicle emissions have multiple aspects. There's greenhouse gases, for example, like CO2, but they also have aspects that is generally associated with dirty air or pollution, like nitric oxides, NOx. And you see that the control here, the dampening of the waves, reduces not just the fuel consumption, it also reduces the emissions. But some emissions are reduced much more substantially. For example, with regards to clean air, this wave dampening is even more promising in terms of the impact. You see a reduction by 74%. And the reason is that with combustion engines, brake, accelerate, leads to very inefficient combustion, and therefore has much, much more exhaust of nitric oxides. So regularizing the flow actually has severe, very, very strong consequences. We also noticed there's a lot of interesting things in these experiments. For example, that the instructions that the drivers are given actually does play a role. In fact, at first, we gave the drivers more or less the instructions: safely follow the vehicle in front of you, as if you were in rush hour traffic. And as a result, we did get these blue data points here. So you see the wave strength here in some measure is down here, and the fuel consumption here is down here. And then we noticed these waves are not as strong as you sometimes observe in some of the videos that we knew. So we gave the drivers the instruction, drive as before, but in addition, place an emphasis on closing the gap to the vehicle in front of you whenever safety permits. In other words, you don't like to have too much of a big gap ahead of you. You drive in some sense aggressively, right? You're impatient as a driver. You drive still safely, but you close gaps ahead of you. And as a consequence, the wave got much stronger here. You got these data points here. And you also see that the fuel consumption went up quite noticeably. So in other words, the driver mindset, how relaxed versus how impatient or aggressive the drivers are, also affects the wave behavior substantially. And of course, that can also be inputted into the models and the simulations as well. Another aspect that in this context is very interesting to look at is that what we tested before was one vehicle that had a carefully designed velocity controller. But as I said early on, existing vehicle technology has adaptive cruise control. So several vehicles you can buy on the market have adaptive cruise control systems. So the vehicle slows down automatically if it has to, because the car in front of it slows down. So one question is, what happens if you take a train, here you have a control vehicle that leads, and then you take a chain of 7 vehicles driving behind, all of which are identical vehicles with an existing adaptive cruise control system that's available on the market. Now, what happens, you see it here, the lead vehicle drops its speed from 50 miles per hour to 44 miles per hour. And as a consequence, the other vehicles slow down as well. But what turns out is, this is all not humans, it's all the adaptive cruise control system. What turns out is that this slowdown actually amplifies. So this is another form of an instability that kicks in here. And it actually goes so far that the last vehicle is actually knocked out of its adaptive cruise control system. It turns itself off once the vehicle gets below 25 miles per hour and then pulls over on the side. Eventually, the system goes back to the correct uniform speed, but at the expense of producing substantial braking that gets stronger and stronger and stronger from vehicle to vehicle. So instabilities are not just something that can happen with humans on the road. It can also happen with some of these automated systems if they're not designed with having stability or instability in mind. So there's still, of course, development to be done on many of these systems as well, and especially understanding, of course, what of these systems are combined with human drivers on the road. Here, likely, human drivers on the road might actually prevent some of these strong braking. At some point, humans might regularize the flow, in contrast to if you have them by themselves being only unstable. Many of these questions are yet unanswered. There's a lot of work to be investigated via models and experiments and other studies. So to conclude, phantom traffic jams and traffic waves that arise on real roads can be explained from the collective driving behavior that happens on roadways. They are caused by instabilities, and that connects them with many other beautiful structures that arise in the world. And in fact, if you're not stuck in traffic flow and you can observe these waves from the outside, they're actually quite beautiful as you see them traveling backwards. At the same time, of course, they are undesirable to the drivers themselves, wear and tear on material, and of course, the increased fuel consumption emissions. So you want to get rid of them. And it turns out that just a few well-controlled automated vehicles can remove these traffic waves. And therefore has tremendous fuel consumption and emissions consequences. So this leads to, in a sense, to a new paradigm. The idea of using automated vehicles for moving traffic flow controllers. So in-vehicle vehicles that are moving. Existing control measures are usually stationary. So ramp metering, having traffic lights on on-ramps that limit the amount of cars that can go in, variable speed limit signs. These are substantial infrastructure investments. Automated vehicles will be on the roadways anyways. So it's almost a free lunch if you can use them for a greater societal good. But of course, the key open question that needs to be researched is the social acceptance by this. So what will be the social acceptance by other drivers, human drivers on the road, of having semi-automated vehicles that drive differently from humans? Either slightly so for increased safety, or noticeably for doing things like flow smoothing. Will the humans invite them to do so? Those are some really important questions that, of course, our research community is looking at, but they're also exciting to see how this goes forward in the next years to come. Thank you very much.
All right, thank you so much for a beautiful lecture. So we can take some questions, and I've noticed that already there were several questions put in chat. So the way we're going to do this is that if you want to ask a question, you can raise your hand, and you probably have a reactions tab. The raise your hand button should probably be hiding in the participants tab, or it just could be available on the bottom of your screen. So go ahead and find it and raise your hand. Meanwhile, let me just take the first question from chat, if I can open it. So this question comes from Will, and the question is, in the AV dampening experiment, do the parameters that govern the single AV's behavior depend on the global configuration, number of cars, speed limit, and so on, or only on the local information? Also, does effective dampening behavior require fast actions?
Yeah, so excellent question. So what turned out in our controllers that we implemented is that we did make use of some non-local information. So we had the vehicle had access to essentially the average speed of the flow of the other cars around it. And those were the different set points that we tried. For practical purposes, probably good controllers will make use of some notion of what is a good speed to try to go with. You want to go with the uniform speed. And this is where vehicle-to-vehicle communication or infrastructure-to-vehicle communication of connectivity can actually come into the game and really improve the controllers. That being said, all we need is an estimate of what is a good speed to go with. What is the average speed of traffic flow downstream of you to go with? So it's a relatively small amount of information that's actually needed. The rest is actually local, and for purposes of safety, it's just measuring the distance to the vehicle ahead and relatively conceptually simple controllers that achieve this. So therefore, these controllers that we implemented, first of all, are not the best controllers that are out there. It's a proof of concept, right? It's showing that something can be done in principle. There's probably better controllers that do it more efficiently, do it by not leaving such a big gap initially, and still can dampen the waves. But generally speaking, having some form of information about what is a good speed to go with has turned advisable. We tried one controller where you look at your average speed from the past, and whenever, of course, you have a ring road, you sort of keep on re-seeing the wave, right, that is traveling around. So if you're on a real traffic flow situation on a highway where you see multiple of these waves, you see these chains, then you could also just try your average speed over the past. But having communication to what is happening downstream is probably superior and will lead to better results.
All right, thank you so much. The next question is coming from Emma. I'm muting you, so you
Hi,
be able
Professor.
to speak.
Thank you so much for your wonderful talk. I had a question about if you could comment on generalizing this from one lane to multi-lane on highways and how opening gaps other cars might want to merge into these lanes. Could you comment about that?
Exactly right. So when I led the talk in the end by saying the social acceptance, that is one of the key aspects that really comes to mind, right? So if you have a vehicle and the vehicle actually does a job of dampening waves, in fact, that doesn't need to be an automated vehicle. It could be a trained driver as well. We tried a trained driver, and some people have done it and even posted videos on YouTube doing this, right? The key concern is, of course, that the car behind it, the driver behind might say, wait a minute, you're not closing the gap. You're not behaving like according to our social norms. So even though the driver does something good, or the car does something good, the person behind it might not perceive it this way, might turn impatient, and therefore try to weave around. But that, of course, might defeat the whole purpose, right? Then cutting in front forces the vehicle to brake for safety reasons. So even though the intent was to be able to dampen the waves, it will be counteracted by the humans around it. So whatever is implemented, there's a lot of different ideas, good ideas out there on dampening waves. One always has to keep in mind, how will the humans around it react to this? And ultimately, that has to be essentially tested on real roads. So the technology needs to be put into a framework where it can be deployed safely on roads, and then one needs to see what are essentially socially acceptable controllers. Absolutely.
Thank you.
Thanks. So our next question is from Matthew in chat. He notes, of course, all drivers are not identical. How much do the mean and the variance of C, the driver's reaction time to change in following distance, change both within and between drivers with alertness and thus with, for example, time of day? And even without any change in mean C, does an increase in the variance of C tend to damp traffic waves?
Yeah, so again, this is an excellent question because, of course, the models, the simulations that I showed were essentially assuming that the drivers were identical, which, of course, all models are wrong. Some are useful, so this still guided us. Obviously, in reality, drivers are different. In fact, even the cars are different that you also saw in the experiments. So this can in principle be tested in simulation. The challenge, of course, is when you look at drivers being different from each other and cars being different from each other, the possibilities are endless. So doing this completely an exhaustive study is actually really challenging. So if one studies anecdotally a few examples of how one can vary something, one generally can nail things down that some of these results of wave dampening and instabilities and wave dampening are relatively robust with regards to variability in the driver behavior within certain limits. Ultimately, the experimental results provide somewhat of a validation that these ideas work, because of course, once you try it in an experiment or potentially even deploy it on real roads, of course, you will see what happens when you deploy it to situations where you have strongly variable systems. And the fact that it doesn't look quite as perfect as in the simulation, but still looks actually quite good in terms of the wave dampening in the actual real experiment. I think this is promising result in terms of that these things probably transfer over to many situations where you have very variable driver behavior.
Thanks. Our next question is from Richard Korf. I'm asking him to unmute so he can ask the question.
Thanks for a very interesting talk. I gather that for an individual driver, the way to contribute to the public good here is just to minimize acceleration and deceleration and try to drive at a relatively constant speed. So I'm wondering if there isn't an opportunity here to sort of educate drivers, if there were sort of efforts to broadly educate drivers on the roads about this. And, the incentive can be, one person isn't going to do it, but it also optimizes fuel economy as well. And I'm wondering, I've never seen it in Los Angeles, where we've got about as bad as it is anywhere in the country. And I'm curious about your ideas about, should we have such a program and would it have an impact possibly?
Excellent question, right? So yeah, could one do a public outreach program that educates drivers on, hey, you can drive in a way to make life better for everybody? Obviously, it doesn't work so well with encouraging people to wear masks in public spaces. So I'm not sure how successful it will be, but maybe it's something that becomes less politically loaded, and there might actually be some success. At the same time, many people take offense in being criticized about their driving behavior, even in the slightest bit. There's something psychological about it. So, and of course, 90% of all or 80% of all the drivers think they're above average drivers, right, in terms of quality and so on. So these typical results. So just anecdotally, based on these things, I would be somewhat pessimistic trying to educate drivers. But what in turn, of course, I think would really be needed is do some public education program about vehicle automation. Because until now, pretty much driving is still sort of what it is, right? It's the system where people somehow pick it up and it actually works surprisingly well as a system. But this is going to change because slowly we get more and more automation. Now we get velocity control potentially being taken over, and that really will change the dynamics. We humans have to get used to that. So I think that is actually more the public outreach, like get used to the fact that there will be some semi-automated vehicles and they will drive slightly differently. And then they will probably also when well designed, have nice benefits on making the flow smooth and so on. It might not even be needed that humans do it, but us learning about how to interact with essentially the little kids, right? So that we need to, when you raise kids, you also change as a person, as an adult. So it's the same with the automated vehicles, right? So we design them, we raise them, but we also need to change ourselves to learn how to work effectively with them.
Thank you. Our next question comes from Colin in chat. He's asking, has everyone looked at how instabilities are created or affected by traffic lights?
Yeah. So city traffic. So pretty much everything I talked about here is highways, where you don't have traffic lights, where you don't have intersections that suddenly slow you down. And in fact, the instability is really something that gets gradually and subtle. So in other words, you have an initially uniform flow, you have very small perturbations, then you have a mechanism for these small perturbations to grow gradually. A traffic light, I would not necessarily categorize as an instability, because a traffic light, when it turns from green to red, actually imposes a very strong perturbation. It's essentially what math folk would call an order 1 perturbation. So it's not small, it's a sudden change to the system that's tremendous. Now, all the cars suddenly are forced to stop. So you cluster them essentially in waves, right? You get the next wave of cars coming, the next wave of cars are coming, but it's almost like that is being enforced by the traffic light control. So it's somewhat of a different aspect of what one would call an instability, which is like there's no immediate discernible cause. One doesn't see immediately why you get these waves happening. So traffic lights are definitely somewhat of a different animal. That being said, of course, there's a lot of work, of course, in understanding how to optimize flow and make it very efficient when you have traffic lights. And in fact, even there's different aspects in the United States, also in other countries, called connected corridors, where you really try to optimize variable speed limit signs, on-ramp, ramp metering, traffic lights on on-ramps, and also traffic lights on arterial roads that lead to and from the highways in a way that you can actually in real time optimize throughput and optimize traffic flow. So yes, there's a lot of interesting work in this direction as well.
All right. Thanks very much. Our next question will be asked by Warren. I think he also asked a question in chat, so perhaps he can ask both of his questions. Warren, I think I asked you to unmute.
Okay. Hello. So there were a lot of work done in physics journals a while ago on this. They used the terms phase transitions and talked about 2 phases and nucleating the phases. They also talked about the possibility of having, they call it superliminal shock waves going backwards, because people also see brake lights. And so there's instances where traffic backups have traveled backwards faster than nearest neighbor interactions, because people see three cars down the brake lights. And so you get these shock waves that can go back very fast. And I wondered if you had any data on that or talk on that. And they also used concepts like, for multi-lane things, they talked about viscosity. In other words, viscosity is how much one lane will drag another lane. So if you have a slow lane, the people in the next lane won't want to go at 60 miles an hour if the lane is 2, but the 3 lanes over, they will go 60. So you can have 20 and 60 if you have 2 lanes in between, but not 60 against 20. I wondered how those concepts are being incorporated, because this was like 10 or 15 years ago, and I wondered whether those concepts are being used or investigated or discarded. I don't know.
Yeah, in a nutshell, there's really a lot of different models out there. So all the aspects you described absolutely are out there in the literature, are being considered, have been studied. Some of them only to the level of theory, of conceptual things, establishing concepts and ideas. Some of them, of course, by looking at real data. Some of them by really also even showing that simulation can be carried out to the real road and even be validated in experiments, for example. So there's a whole level of ideas out there. In terms of phase transition, essentially this critical parameter C that in the very simplistic model that I laid out, essentially that leads to a phase transition. So if the C is so that uniform flow is stable, right, that is what you will observe. At the moment where you go below that critical threshold, you suddenly will get that the system actually gets to a wave state. So that really can be seen actually as a phase transition, right? From solid to liquid, for example, or from solid to gas, or some analogy. So these kind of waves already model phase transitions. And they do it sort of, it's not being explicitly put in. It's a consequence of this transition from stable to unstable. There are also traffic models. There's a lot of fluid dynamical traffic models where you really don't describe individual vehicles, but describe the traffic density and traffic velocity field in equations that essentially resemble gas dynamics and fluid dynamics. And there are models that intrinsically produce phase transitions. There are models where phase transitions are explicitly put in. They're even called phase transition models. So there's all kinds of aspects. Aspects like interactions across lanes, obviously viscosity effects are plausible to happen. More important, obviously, is lane switching across different lanes. And again, this can be described in a micro simulation model of vehicle specific. It can be described in a fluid dynamical model. So all of these phenomena have been looked at and have been studied. With regards to understanding traffic flow, with regards to, for example, putting automated vehicles for greater good, of course, the key recipe to remember is also that reality is always really, really complicated. What aspects of reality do we need to model? So again, the philosophy always has to be, what is the simplest model that captures what you care about? So is there an effect like viscosity even without lane switching across cars? Maybe yes, maybe no. It might even be very dependent on where you are and broader context of a situation. Is it needed to demonstrate the flow smoothing? So far, we have not needed it. Yeah, so that would be an example of an effect that is not there. Lane switching, of course, on the other hand, is probably very important. Yeah, so if you have an on-ramp or an off-ramp and cars have to switch lanes, or they do it tactically to get to a lane that moves a little faster, ultimately, all these aspects have to be considered when one does flow smoothing. And in fact, this is ongoing work that we also consider.
Thank you so much. We'll probably go through a couple more questions in chat. One from Sasha, thought-provoking lecture. Have dampening being studied from a game theoretic angle? I wonder if drivers moderate their gap clothing behavior, act in self-interested way in terms of improving their average speed. Clearly, it's better for fuel economy.
Mm-hmm. Yeah, so first of all, in fact, there in this program that we have at IPAM right now, in fact, there have been several presentations on mean field games, so game theoretical approaches to understanding traffic flow when different agents have different objectives in the flow. The specific example on gap closing behavior from a game theoretical point of view, I have not seen directly. The main challenge in creating a model that is predictive of reality is that you need a good model of how the other humans will react to some drivers behaving noticeably differently. So one probably needs better data first collected to understand this aspect so that the model will actually predict something about reality. That being said, in principle, of course, then this is a natural aspect to bring in game theory because you have different agents. For example, humans who are aware that this car is trying to do flow smoothing and are trying to be supportive, whereas others that are really annoyed by it and try to cut in front of it. In fact, there have even been examples in some test places, California, where humans have started bullying self-driving cars, knowing, oh, this car is not going to hit me. I don't need to let it in. I can just prevent it from going in. So they have even aspects of people bullying cars or playing with them and toying them. So the human behavior around these automated vehicles is extremely interesting and extremely important to study.
All right, thank you so much. Next question came from Mohammed. Can we show this traffic situation to be chaotic by using some mathematical modeling?
I am always a little hesitant to call the traffic system chaotic because if you, in my view, a chaotic system is one that really has to establish some form of a Feigenbaum diagram, so period doubling and intermittency and so on. So I would not go that far that real traffic explicitly shows all these manifestations that you have in really chaotic systems. That being said, the nature of the instability is of course something that ultimately people associate, sometimes call butterfly effect, right? So you have a very, very tiny perturbation to your initial state, but then it can of course lead to severely different consequences on what the system does. For example, one scenario could get like a wave being here, and another one could have a much bigger wave being at a different place, and there's no way to predict where the wave will be when, in the same way as you cannot really predict on this second tomorrow, will there be a wave crest or will there be a wave valley hitting you at this second, right? So something like this butterfly effect in a sense also arises intrinsically whenever you have an instability. You cannot predict a priori where the Grand Canyon will form exactly. You just know that somewhere in this area, when you have the mechanisms that drive it, it will form somewhere there. So in that sense, traffic waves have exactly that phenomenon. Yes.
Right, so I think we have like 3 questions left. One question was from Shima writing, I was wondering if a control policy that ensures the string stability will avoid collision as well or not?
Short answer, not necessarily. So just ensuring string stability, so making the system stable near equilibrium, does not ensure that you avoid collisions under all circumstances. So string stability in a nutshell means that the perturbation that one vehicle had does not get amplified from vehicle to vehicle, but that is generally a statement about small perturbations from equilibrium. Whether you can collide to the vehicle ahead of you ultimately is a question about the nonlinear regime when you have large perturbations. So if you are, for example, first of all, if you're slightly unstable and you get perturbations, then of course you have to additionally make sure that you don't collide. But the main point is that string stability doesn't guarantee that your system will always stay close to equilibrium, because of course you have other things going on. You could have a whole stretch of cars without a control vehicle nearby, then of course you will get waves happening. The next vehicle wants to dampen them, but the perturbations are big. You of course have lane switching. You could have a driver once in a while tapping their brakes unnecessarily because they have been dreaming or looking at their phone. So perturbations always happen. So ensuring string stability is not alone. You always have to make sure that you also ensure that whatever you implement is definitely safe in the large perturbation regime.
Another question from Dmitry asking, can you give a science perspective on where is Tesla with their semi or fully autonomous autopiloting system?
Not really, because of course nobody knows exactly what's in there unless you work for Tesla. The main thing I want to say is that it is bad to call a cruise control system, no matter how advanced it is, autopilot, because it is misleading humans. That is a misnomer. That actually is dangerous. That being said, in terms of what the vehicle is capable of doing and the circumstances under which Tesla vehicles, and in fact also other vehicles that are designed out there by Waymo and Uber and so on, they really work well, I would say, in 99% of all the cases. So they can do very convincing stuff in in demos in usual situations. The key thing where I said that fully autonomous vehicles, level 5 autonomy, is still a thing of the far future, is because it's the corner cases. It's the very rare but important cases where you need to make sure that you still can ensure safety. And this is still a far stretch to work. So that's why when you buy a Tesla, you agree that you are able to take over at any instance in time as a human if the vehicle doesn't know what to do anymore. And of course, that is in itself a key question of how good are we humans at a task that most of the time the car is doing the job for us, and then suddenly within a second we have to suddenly take over, right, and assess it. Well, that might actually be hard. So that is another key challenge, right, to understand how valid are these semi-automation, level 3, level 4 automation, and how safe are they, given that the human must be able to take over? Are humans actually capable of doing this? In a sense, there's an experiment going on with some of these cars, and time will tell But the main point is that many of these technologies are very good in almost all the cases, but it's the almost that makes the real difference to prevent them from being fully autonomous.
All right, thank you so much. We have one question left, but before that, I just want to thank everybody for taking part. It was really a wonderful turnout. And Benny, thank you so much for giving a wonderful lecture and in detail answering all the questions. So the last question is from Johnny. He says, I would model multi-lane hopping simply as a single lane traffic with spontaneous creation and annihilation of cars. Is your model easily extendable along such a path? And is that what's commonly done? Is that a good approximation?
Whether it's a good approximation to reality or not, it depends on how exactly it is being done. And ultimately, it has to be tested, right, validated against real data. What is commonly done when people do microsimulation, where they really care about the trajectories of all the vehicles and the intricate details of how a road geometry of an on-ramp affects things, is really microsimulations where you explicitly describe the different lanes and explicitly describe the mechanics of how cars move between lanes. So this is generally what's called microsimulation. There are tools which people buy out there. There are also publicly available open source projects, like one called Sumo, for example. That is what is commonly done if one really is interested in the details of the lane switching. So it's explicitly modeled. If one is interested in aggregate quantities, aggregate consequences, then usually people oftentimes use macroscopic models that essentially assume that vehicles can somehow move around each other within certain limitations, but they don't actually aim to explicitly model the lane switching at all. It's a lane aggregated model where there's some mechanism for traffic density to evolve in certain ways. What you outlined would somewhat be a middle ground. That, again, does not mean that it is a bad model at all. After all models are wrong, but some are useful. So ultimately, you would need to test in your model whether it's useful.
All right. Again, thank you so much. It was really a wonderful, wonderful event. Benny, thank you so much again for sharing your wisdom. And everybody, I just want to wish you a very happy and safe week and happy holidays. Thank you so much.